Good afternoon, students. Welcome to this session of Applied Thermodynamics. Today's topic is compressible flow. We will solve one numerical problem in this topic. The problem statement is as follows. Products of combustion enter a gas turbine with a stagnation pressure of 0.9 megapascal and a stagnation temperature of 840 degrees centigrade, and they expand to a stagnation pressure of 100 kilopascal. Taking K equals to 1.33 and R equals to 0.287 kilojoule per kg Kelvin for the products of combustion, and assuming the expansion process to be isentropic, determine the power output of the turbine per unit mass flow. So the problem is, there is a gas turbine. At the inlet, the stagnation pressure given as 0.9 megapascal and the stagnation temperature given as 840 degrees centigrade, and it is expanding at the exit at a pressure of 100 kilopascal. The specific heat ratio value given as K equals to 1.33, and the characteristic gas constant given for the product of combustion is 0.287 kilojoule per kg Kelvin. You see that this value is given same as that of air. Now consider that the expansion from the inlet up to the exit is isentropic. We have to determine the power output of the turbine per unit mass flow rate. So we will see what are the given data. For this problem, the given data, the device is a gas turbine. At the inlet, the stagnation temperature is given as 840 degrees centigrade and stagnation pressure is 0.9 megapascal. At the exit, the stagnation pressure is 100 kilopascal. The specific heat ratio is 1.33 and the characteristic gas constant is 0.287 kilojoule per kg Kelvin. The process is isentropic between the inlet and the exit. Now see that why the stagnation properties are given instead of the actual values of the properties, that is temperature and pressure. So far we have never seen that the property values are mentioned as stagnation, temperature or pressure. Now we see that why this is so. Now see that when the probes are inserted in the flow, the recorded value, the probes will actually act as an obstruction in the flow field. You see in this slide that, say this is the probe, that is the thermometer. When it is placed in the flow field, it will be acting as an obstruction in the flow field. Therefore, the flow which is moving like this, it will be stopped fully at the tip or at the bulb of the thermometer. So the velocity will be converted to, or the kinetic energy will be converted to the thermal energy, or corresponding the momentum will be stopped. Therefore, whatever temperature and pressure will be recorded will not be the actual value. You see, it is showing here the temperature actual in the flow is this, but when it is stopped by the thermometer, the temperature increases. So the actual temperature, that is 300 Kelvin, will be increased to 305 Kelvin, say, by the obstruction created by the thermometer. Therefore, the value that is recorded by the thermometer is not the actual value of temperature. Similarly, for the case of pressure measuring device or the pressure gauge or pressure sensor, therefore the value that are given are stagnation temperature and stagnation pressure instead of the actual values, because the probes will measure, or probes will display the stagnation properties instead of the actual properties. So that is what I have written here. The stagnation properties are given because the probes may act as obstructions to the flow, and therefore the recorded value of the properties will include the effects of kinetic energy per unit mass, that is V square by 2g. We know that the stagnation temperature is actual temperature plus the temperature rise due to the kinetic energy. So you see that this is having effect in increasing the temperature. Similarly, it will have effect on increasing the pressure. Now we move to the next slide. In this problem, the objective is to determine the work output or the power per unit mass of the products of combustion. Now to determine this, let us see what is the control volume. Say this is the control volume, that is the gas turbine. I have shown the control volume with the dashed lines. This is the inlet to the turbine. This is the exit from the turbine. Inlet is denoted with I and exit is denoted with E. The turbine is producing shaft work W dot per unit mass flow rate, that is when it is divided by m dot, the work output is small w. So that is to be determined. Now the assumptions. The process from inlet to the exit in the gas turbine control volume is isentropic. Since it is reversible also, so this is adiabatic, therefore heat transfer to or from the turbine, that is the control volume, is 0. So the heat transfer is 0. Now another thing is the potential energy and its change are negligible compared to other energies. Potential energy is m dot g z per unit time. So we consider that the changes in elevation is negligible and its absolute magnitude is also negligible compared to the other energy terms like say kinetic energy or say enthalpy or heat transfer or work transfer, etc. So that is why we have neglected that to be 0. So potential energy is neglected. Now if we write the steady flow energy equation, another thing that definitely we have to assume that it is a steady flow device. So if we write the steady flow energy equation, it is Q dot plus mass flow rate at the inlet multiplied by enthalpy at the inlet plus kinetic energy plus potential energy. Potential energy we have already neglected, so that is 0, equals to mass flow rate at the exit multiplied by enthalpy at the exit plus kinetic energy at the exit plus potential energy at the exit, and that is again 0, plus W dot, that is the work transfer per unit time. So if we consider the mass flow rate at the inlet, mass flow rate at the exit are same from the mass conservation. If we consider that is same as m dot, then we can divide both sides of the equation by m dot to get this one. This is hi plus vi square by 2 equals to he plus v square by 2, and w dot divided by m dot is w. You see, w dot divided by m dot is w. So we have written the equation on the basis of per unit mass flow rate. Now remember that this hi is actual enthalpy at the inlet, he is the actual enthalpy at the exit. Now therefore hi plus vi square by 2 is h0i, where h0 is the stagnation enthalpy. So H0I is the stagnation enthalpy at the inlet. Similarly, He plus V square by 2 is stagnation enthalpy at the exit. So H0I equals to H0E plus W. H0I equals to H0E plus W, that we have written. Therefore, W is equal to H0I minus H0E. Since the product of combustion is an ideal gas, therefore we can write it to be Cp into T0I minus T0E, where T0I and T0E are the stagnation temperatures at the inlet and exit. Now, you see that in this problem, therefore, to determine the work output, we need to know what is T0E. All other quantities, that is Cp, T0I, are given. How to determine Cp? Cp is equal to K R by K minus 1, where K is the specific heat ratio. Remember that Cp by Cv is K and Cp minus Cv is R. So you can calculate what is Cp in terms of R and K. So you will get this. K is given as 1.33 and R is 0.287 kilojoule per kg Kelvin. K minus 1 is therefore 0.33, and you can determine that to be 1.157 kilojoule per kg Kelvin. Okay. Now go to the next slide. So we have to determine the value of T0E. Now we know that the relation between the actual temperature, stagnation temperature, and actual pressure, stagnation pressure is like this, because the process of stopping the flow is an isentropic process. That is the stagnation process we assume to be isentropic process. So if we have one probe, say thermometer, like this, then the flow is moving. So between this point and this point, the process is assumed to be isentropic. So here the property is the actual property. Here the corresponding property is the stagnation property. So if we write the isentropic equation between these 2 points, then we will get this. So it is P0i by Pi equals to T0i by Ti to the power k by k minus 1, where P0i is the stagnation pressure corresponding to Pi and T0i is the stagnation temperature corresponding to Ti. So this is written at the inlet of the turbine. Similarly, we can write the expression at the exit of the turbine. So P0e by P equals to T0e by T to the power k by k minus 1, where P0e is the stagnation pressure corresponding to P and T0e is the stagnation pressure, stagnation temperature corresponding to T. So this is written at the exit. Now again, the process between the inlet and the exit is isentropic. Therefore, we can write similar expression between the inlet and the exit of the actual property, that is Pi by P, Pi here, P here, Pi by P is equal to Ti by T to the power k by k minus 1, where you have to remember that this Pi and P, they are nothing but the actual value of pressure here and here. Ti and Te are the actual value of temperature here and here. So we can also write this expression because the process is isentropic. Now remember that we have to determine T0E from this. Now what are given? P0I given, T0I given and P0E given. So all the actual properties are not given, therefore we have to arrange the expressions in such a way that they will cancel. So what we do is we multiply the left hand side of all these expressions together and multiply the right hand side of all these expressions together, so that the values Pi, P, Ti, T are cancelled. So what we do is, here I have written P0i by P0e, P0i by Pi directly. Now here I have just written the reciprocal, that is Pe by P0e. For this I have taken it directly, that is Pi by P. On the right hand side, therefore this will come directly, T0i by Ti to the power k by k minus 1. Since I had taken the reciprocal of this, so here it will be reciprocal of this. So it is T by T0e to the power k by k minus 1, and this will come directly, that is Ti by T to the power k by k minus 1. I think it is clear. Now you see that if we write like this, then this Pi will cancel, P will cancel. We have to do this because these values are not known. We have to reduce the number of unknowns. Similarly here Ti cancels, Te cancels. Okay, so after doing this, the remaining term here is P0i and P0e, both are known. On the right hand side, T0i and T0e. You see that T0i is known, T0e is unknown. So if we write this, then it is P0I by P0E on the left equals to T0I by T0E to the power k by k minus 1 to the right. Only one unknown in a single equation, so it can be solved. So from this equation we can determine what is T0E. So remember that we have to determine W as Cp multiplied by T0I minus T0E. So we have to determine T0E. In the last page we have seen that P0I by P0E is T0I by T0E to the power k by k minus 1. So if we transfer the power from the right towards to the left, it will be T0I by T0E is equal to P0I by P0E to the power k minus 1 by k. Therefore, T0E equals to T0I multiplied by P0E divided by P0I. There is a mistake, it will be P0I, remember. Here it will be P0I. So T0E equals to T0I multiplied by P0E divided by P0I to the power k by k minus 1 by k. So all the terms on the right hand side are known. T0E is 840 degrees centigrade. We have to use the Kelvin because this comes from the ideal gas relation, and P0E is 100 kilopascal, P0I is 0.9 megapascal, that is 900 kilopascal, K is 1.33, so 0.33 divided by 1.33, the value in Kelvin is 645.34 Kelvin, and in degree centigrade it is 372.19. So W is Cp multiplied by T0I minus T0E. All are known. Cp we have determined earlier to be 1.157 multiplied by T0 840 degrees centigrade and T0E 372.19 Kelvin, 19 degrees centigrade. So the work output per unit mass flow rate is 541.25 kilojoule per kg. Remember that we can use either degree centigrade or Kelvin for this calculation. Thank you.